This section deals with rational functions. So let's begin by defining what a rational function is. A rational function is a function that can be expressed as a ratio of polynomial functions. So ratio just makes us think of fractions. So it's a function that is actually a fraction, and it can be expressed as a polynomial divided by another polynomial. So we typically think of it as f of x is equal to p of x over q of x, where both p of x and q of x are polynomials, and the only thing that we say is that q of x, or the denominator, cannot equal 0. And the reason for that is, again, as always, division by 0 is undefined. So let's talk about the domain. And remember, domain is all the x values. So domain, recall from before, is the x values. So the domain, or the x values of a rational function, so everything that you can plug into a rational function, is all real numbers except any of those where the denominator is equal to 0. So again, it's all real numbers except any real number which makes the denominator equal to 0. And again, the reason for that is that division by 0 is undefined. So how would you find the domain of a rational function? Well, the very first thing that you do is you set the denominator of the function equal to 0 and you solve for x. Any real numbers, and only real numbers, but any real numbers that you obtain must be excluded from your domain. So let's look at the first three examples where we're finding the domain of a rational function. So example 1 is f of x is equal to 6 minus x over 2x plus 1. So let's find the domain. Well, the first thing I need to do is set the denominator equal to 0 and solve for x. So I set the denominator, which happens to be 2x plus 1, equal to 0, and I solve it for x. Well, if I solve this for x, I end up with x is equal to negative 1/2. So there's two ways that we can write the domain. The first way is in set notation, and the second is in interval notation. Let's take a look at set notation first. What we would say for set notation is that domain of the function, so the domain of f, is going to equal x such that, so this line here, this vertical line means such that, so x such that x does not equal whatever number or numbers we just obtained. Well, we only got negative 1/2, so we say that the domain of the function is equal to x such that x does not equal negative 1/2. Alright, well, the second way I said we could do it is interval notation. So let's take a look at interval notation. And honestly, the easiest way to think of interval notation is from a picture. So let's put this information on a number line and then go from there. So if what I'm saying is that x can't be negative 1/2, if I were to look at a number line, basically I would have an open circle at negative 1/2, and I would have everything else shaded. Well, if I want to write the domain of the function given this picture, I would say that the domain of f is equal to negative infinity, because the leftmost part of the number line is shaded, all the way to negative 1/2 with a parentheses because it has an open circle, union, pick back up at negative 1/2 all the way to positive infinity. So the domain of the function written in interval notation would be negative infinity to negative 1/2, union negative 1/2 all the way to positive infinity. And either one of these answers, either set notation or interval notation, is accepted. Let's look at example 2. Again, same thing. Find the domain of this function. Well, the first thing we need to do is set the denominator, which happens to be x squared minus 9, equal to 0, and solve for x. Well, if I solve it, I can move 9 to the other side, and I'd get x squared is equal to 9. Take the square root of both sides, and you end up with x is equal to, don't forget, when you take the square root of a function to solve it, you write plus or minus. So x is equal to plus or minus 3. So for set notation, we would say that the domain, and this happens to be g, the domain of g would equal x's such that x does not equal, again, whatever numbers we just obtained. Well, the numbers we just obtained are positive and negative 3, so we would write plus or minus 3. All right, let's look at it again as interval notation. And again, it's easier to look at that if we put it on a number line. So the two numbers that I'm saying that I cannot be are negative 3 and positive 3. So I would have open circles at negative 3 and positive 3, and the rest of my number line would be shaded. So if I look at that number line to help me write the domain in interval notation, I would get that the domain of g is equal to negative infinity to negative 3 with a parentheses because of the open circle, union, then between negative 3 to positive 3, again with parentheses because of the open circles, union again, 3 to infinity. All right, let's look at example 3. First thing we do, set the denominator of the rational function equal to 0 and solve for x. So I'm going to set the denominator of x squared plus 9 equal to 0, and I'm going to solve it for x. So I end up with x squared equals a negative 9. Taking the square root of both sides to solve, I get that x is equal to plus or minus 3i. Then, the second step here says any real numbers obtained should be excluded. Well, let's take a look at this answer. Is this a real number? No, it's not a real number. It's an imaginary number. So, because it's an imaginary number, it doesn't have to be excluded. So, if I have no exclusions, that means that the domain of my function, h, is going to be in interval notation negative infinity to positive infinity, or we could say just the r like this for all real numbers. So because there's nothing to exclude, and there's nothing to exclude again because it's an imaginary number, and we don't have to exclude imaginary numbers because they're not real numbers, then the domain would be all real numbers. And again, either way is an acceptable format for writing that. Alright, well, we talked a little bit about domains of rational functions. Let's actually graph a rational function just as an example of what one looks like. So I want to sketch the graph of f of x is equal to 1 over x. And I'm going to do that by making a table of values. So let's pick some numbers from my table of values. I'm going to plug in negative 2, negative 1, negative 1 half, 0, positive 1 half, positive 1, and positive 2. Well, let's figure out what happens when I divide here. And just to save time, because again, you can use any calculator, and all you need is a little scientific one, I'm going to use the one from the computer here, and I'm going to do the division. So I have 1 over negative 2, and I really didn't need the calculator for this, but I have 1 over, the way that this one works is I said 2 and then negative, hit enter, and I get negative 0.5 or negative 1 half. And I'm going to write negative a half. Next one, negative 1 or 1 over negative 1. So 1 over a negative 1 gives me a negative 1. Next one, 1 over, and I'm going to write the parentheses because it's going to be divided by a fraction. So divided by, and then I have negative 1 over 2. Close my parentheses, and I get that that's equal to negative 2. 1 divided by 0. I should get an error. I do. Look at it. It says cannot divide by 0. You cannot divide by 0. We all know that that's undefined. Next one, 1 divided by a half. We end up with 2. 1 divided by 1, we should end up with 1. And then 1 divided by 2 is a half. So let's graph all these values on this coordinate system. So the first point I have is negative 2 and negative a half. Let's have all of these count as a half. So here would be negative a half, negative 1, negative 1 and a half, negative 2. Same thing here, negative a half, negative 1, negative 1 and a half, negative 2. Here's positive a half, positive 1, positive 1 and a half, positive 2, and then positive a half, positive 1, positive 1 and a half, and positive 2. All right, let's go plot these points. I have the point negative 2, negative a half, so negative 2, negative a half goes right there. Negative 1, right here. Negative a half, negative 2, right there. 0, undefined, so I can't plot that point because it cannot plot undefined. 1 half 2, half 2, and 1, 1, 1, 1, and finally 2 and a half, 2 and 1 half. Notice we have a big jump here, so we're going to plot these 3 points on the left and put arrows on them, and then plot these 3 points on the right and put arrows on them. Now the reason that I'm doing this, and I know that it's going up and I know it's going this way, is I know this graph, but let's say that we didn't. So as I go more and more left this direction, right, let's pick a number very left. So let's say that I do, I don't know, negative 1,000. So x would be negative 1,000, so I would divide 1 by 1,000 negative. Alright, well that's a number that's very, very close to 0. Well, as I go more and more left here on my x-axis, I'm getting closer and closer and closer to 0. Well, what about as I get closer and closer to x equals 0? So let's pick a number negative. From over here it would be like negative 1 over 1,000. So I would divide 1 by parentheses negative 1 that over 1,000, and I'd end up with negative 1,000, which means I'd go further and further down the y-axis. The same argument can be made for the other side, which is why this graph goes closer to the x-axis as I move to the left and closer to the x-axis as I move over here to the right. And it's also y, it gets closer to the y-axis as I move down closer to 0 from the left, and closer to the y-axis if I move up closer to 0 from the right. So let's talk about the domain, and then we're going to talk about these things called asymptotes that I was just trying to explain. So what's the domain of the function? Well, we know how to find that. What do? We set the denominator equal to 0 and we solve for x. So I set the denominator equal to 0. Well, it's already solved for x, and I'm just going to write this in set builder notation. So I would say that the domain is x such that x doesn't equal 0. So that means that my graph can be any number except for I can't plug in a 0 in for x. Well, if I can never plug in a 0 in for x, then I can never be 0. Well, why is that? Well, that's because this is called a vertical asymptote. It's vertical because it's up and down. So I actually have a vertical asymptote at this line. Well, what kind of line is this? Since it's a vertical line, it's x equals 0. So I have a vertical asymptote for this function at x equals 0. Why? Because I can never be 0. And why can't I be 0? Because the only way that I can be 0, the only way that x can ever be 0 is if division by 0 was allowed. But it's not allowed, so I can never be 0. Well, if I take a look at this, how do we get 0 as an answer? So how would y ever be 0? The only way is if I would have 0 divided by a number. But can I plug in a number in for 1? I can't. Because I can't plug in a number in for 1, or because the numerator doesn't have a variable, I'm never going to get 0 as an answer for this function. And that means that I'm going to have what's known as a horizontal because it's this horizontal line at y equals 0. So I have a horizontal asymptote at y equals 0. So again, let's take a look at this. We graphed f of x equals 1 over x. Rational functions usually have these jumps or breaks, and they usually have these asymptotes, things that they want to get close to but don't. And we're going to define in the next video how to find asymptotes, but I want to talk about what asymptotes are right now and then relate them back to the picture. So an asymptote is a line or a curve that your graph wants to get close to. So it really wants to get close to that line, and that's going to be as it heads to infinity or actually as it heads to 0. But usually your graph can't touch or cross it. I'm going to talk about why in the next video. But again, asymptotes are lines that your graph is approaching. So here, my graph is approaching the line y equals 0. And again, from the other side, my graph is approaching. It wants to be 0, but it's never going to get there. And it's never going to get there. And because it's never going to get there, it has an asymptote. In the next video, we're actually going to talk about how to find asymptotes of rational functions.